This data represents the numerical value of the graph that I was just showing. We thus should be able to look at these numbers and come up with the Km and Vmax, which are two characteristics of an enzyme that are highly relevant to biochemists. As shown in these numbers, when the substrate amount is 2,000 micromoles, the velocity is 155 micromoles per minute. From the graph, I estimated 155, and 155 seems like a good number to choose based on this data for a Vmax. 155 divided by 2 is just under 80. So I will round off to 80 because it is a velocity that is present on the graph. And the substrate value at 80 micromoles per minute corresponds to 60 micromoles of substrate. From the graph, I had estimated this value at 100 micromoles, so these two numbers seem to support each other. On this graph, I have a different set of data. I would challenge anyone who told me they could look at this graph and determine the Vmax, especially in the days before computers and the work of Michaelis-Menten and Lineweaver-Burke that we're about to talk about was being done in the 1920s. A mechanism had to be developed for more precisely determining Km and Vmax values than we have just been doing. The most commonly used method is for transformation is that of Lineweaver and Burke. The transformation is to take the inverse of the Michaelis-Menten equation, which yields the equation shown here. When this is plotted as y equals mx plus b, the slope of the line obtained is equal to Km over Vmax divided by Vmax, though this is not particularly useful. Instead, the intercepts are extraordinarily useful. The y-intercept of a graph of this data represents 1 over the Vmax plus b, and the x-intercept represents minus 1 over the Km, because we're plotting 1 over S, substrate concentration. This table represents the values derived from the preceding data, just to show you the data that I am going to be using for the graph. And this graph shows what the data looks like. It will be noted that although it is easier to get these intercepts, it is not a trivial matter. With the technology that we have today where we can zoom in on part of the screen, it's a lot easier than it was in the old days. The Lineweaver-Burke plot does have some shortcomings, one of which is immediately obvious from this graph. That is, there is a point at y equals 0.20 and x equals 0.5 that will very much influence where we draw the line through these data points. Note that that point is derived from our second lowest substrate concentration, which is our least precise experimentally determined data point. Why do we care about the Km and Vmax? The Km is a measure of the affinity of the enzyme for the substrate. In other words, if we know the concentration of glucose in the bloodstream, we will know how fast the reaction using glucose should go. Usually, the physiological concentration lies somewhere between 0.1 times the km, and 10 times the km. A graph of two enzymes illustrates this point very well. This graph is a plot of velocity as a function of blood glucose concentration. The physiological concentration of blood glucose is around 100 milligrams per deciliter, as illustrated by the black lines. The enzyme hexokinase, the upper green, is maximally active throughout the physiological blood glucose range. It's operating at 100% activity. This is consistent with its function, which is to phosphorylate glucose upon entry into the cell so that the glucose does not exit the cell again. In contrast, the function of glucokinase is to regulate blood glucose levels. Its activity can increase as glucose rises after a meal, and this would allow the glucose to be stored in either glycogen or fat according to the body needs. Conversely, its activity would fall if glucose levels falls, as it would between meals. The next question to consider would be, what is the perfect enzyme? Another characteristic of enzymes is their catalytic efficiency, which is abbreviated as kcat, and also referred to as turnover number, which has units of molecules per second. This measures the speed of an enzyme, which can reach astonishing rates. But if substrate is not available to the enzyme, then the rate cannot be fast. Therefore, the best way to compare enzymes is with the ratio of kcat divided by km. An enzyme with a large kcat and a high affinity, in other words, a small km for enzyme, would have an exponentially increasing catalytic efficiency. Let us next turn to an examination of what things affect enzyme rate. As shown in this graph, and previously shown earlier, substrate concentration is one thing that has a profound impact on the velocity of an enzyme reaction.